So this is a little review. We talked about Venus. We talked about the Earth, and we were just getting to the mechanism of the greenhouse effect, and when time ran out. So I'm going to just finish that up. Let's just do a little review, and right away I'm going to do an aside because I think it's interesting. We have had over 42 missions to Venus, so we know a lot of things about Venus. And there's this surprising contrast that the planet of Venus and the planet of Earth are not very different in size, in gravitational attraction. Venus is obviously a little closer to the sun than the Earth, and that has some significant effects. But, these 42 missions have been really remarkable in what they tell us about it. And they tell us that it's extremely hot, that has an atmosphere that's 90 times denser than Earth's. But I wanted to mention that quite a few of the 42 missions were not actually intended to go to Venus. We use Venus as a swing point for several other missions. To get a satellite in orbit around Mercury, we used 5 flybys of Venus to change the orbit, this sort of ricochet effect. And each one of those brought you close enough to Venus to take some pictures. And so we'd get some data about Venus, even though what we were really doing was going to Mercury. And right now we have something called the Parker Solar Probe. And the plan with the Parker Solar Probe is to have it, I think it is already in orbit around the sun. And then we use Venus to change that orbit. So it goes successively over 7 different flybys of Venus. It goes to successively closer orbits to the sun with final destruction. I mean, we're just trying to see how close we can get to the sun with this probe before it burns up and or just goes useless. And that's where this picture comes from. This is from one of those flybys. I thought that was kind of a neat thing. But the real point I wanted to make here is that despite the similarities in shape, as I mentioned, the atmospheric pressure of Venus is 90 times that of the Earth. Its atmosphere's gases are 96% carbon dioxide, 3% nitrogen, where Earth is 78% nitrogen, 20% oxygen. And we'll come back to that again. Not much water on Venus, a lot of water on our planet. And as maybe you'll hear from Jerry and Carl and Mike, that water turns out to be really our life's blood in a very profound way. But the surprising thing is that Venus has a surface temperature which is 743 kelvins or 470 centigrade. I should probably put that in Fahrenheit, talking to a general audience, but it would take me too long to think it through. And 288 Kelvin. This is kind of a key number when you talk about Earth and its properties. And it's a key number because of the other thing which we did was talk about the radiation balance of Earth, because it's crucial to any planet that we're looking at. Where does the energy come for a planet and what happens to it? That's what's going to determine the temperature, at least to what we call maybe the 0th order approximation, something like that anyway. So this curve, the Planck function, which tells you how much energy is arriving per square meter as a function of, and I'm using wave number, other people use wavelength, other people use frequency. I like wave number because it's a smaller number than frequency. It's actually proportional to frequency. I like wave number because it goes from low energy down, whoops, I didn't mean to do that. Goes from low energy down at the 0 up to high energy at the higher wave numbers. This is a kind of basic radiation distribution, how much is coming out at each different frequency, each different wave number. So for Earth, And this is a curve for 260 Kelvin. It's a little cooler than the average temperature of Earth, but still not that far off. So for Earth, you can see the peak of energy comes in at about 600 wave numbers. A little up here from 500, 600, 700, 800, 900,000. So you get a sense of that the Earth radiates in the microwave. This is also in wavelength. It's about 15 microns, and when we use that, and again, I did the calculation. I won't do it again, but I'll just remind you of the result. When you say if there's no atmosphere on our planet, you're going to get and the planet reflects 30% of the light that's coming in, so that only 70% is absorbed. Then it turns out, very simple calculation from very basic physics, the equilibrium temperature for Earth is 255 Kelvin, which is minus 0.4 degrees Fahrenheit. So cold, that would be very cold. And we would be a snowball, or maybe just a giant ball of ice. And the thing that's interesting is if you do the same calculation for Venus, even though Venus is closer to the sun and has twice the solar flux coming in, it is, at least in the present situation, highly reflected. 80% of the sun just reflects off the cloud base, and only 20% is absorbed. So even with double the incoming flux, if you take the so-called the absorbed insulation, you come out with a temperature that's colder than Earth, 220 Kelvin. But and in each case, back here, I didn't write down the actual temperature, but I mentioned already the actual temperature for Earth is about 288, not 255. And that makes a lot of difference to us. But on Venus, it's 743 Kelvin. I mean, it's up in 500. It's hot enough to melt lead. And this striking difference is what really the talk was about last time. And why is it? I mean, so it has to come from some difference between the two planets, how they get to be. I mean, two questions arise. One, why are they so much warmer than just simple radiation balance? And why is Venus so spectacularly much warmer? And in the end, I'll express my disappointment with my explanations, but I'll go on right now and talk about a very simple model of how an atmosphere warms the surface of a planet, because that's really what's going on. It's clear that the atmospheres of the planets have a tremendous effect on what happens at the surface. And in a way, you can think, sure, that makes sense, because a lot of the radiation that comes from a planet comes from the upper parts of the atmosphere. And the upper parts of the atmosphere are quite cold. So in a way, you're going to live by that simple model that I showed you before, that, let's say, the Earth is going to be radiating from something rather cold, 255 Kelvin, because it's going to be coming from the top of the atmosphere. And the surface is radiating stuff too, but the atmosphere is catching that. So I want to just go through a very simple, much oversimplified, does not explain a lot of what we would like to explain, but it will show you kind of very simply how the surface ends up being warmed by the atmosphere. Everybody with me on that? All right. I always wonder if I'm talking to myself.
So far, so good.
Okay, thank you.
Well, of course, you're always talking to yourself, but luckily there are others of us that are also listening.
Yeah, well, the cursive Zoom is often that's the only person you're talking to sometimes. Anyhow, all right. So this little model is very much oversimplified, but it tells you what I want to show you. So here's the sun, okay, and here's the Earth. this green-brown thing. And I'm saying that the sun is radiating onto the Earth, 1 unit, arbitrary unit. We could call it a rudi, all right? So we're radiating in 1 rudi, which is a lot of watts per square meter a lot of joules per second per square meter. And
What?
yeah, watt. Yeah. And so the Earth has to get rid of that. And as I said, ultimately, the only way a planet can get rid of, for most practical purposes, the only way a planet can get rid of energy is by electromagnetic radiation. It has to send it out as microwaves. It has to send it out with whatever distribution corresponds to its temperature. So if you put 1 rudi into the Earth, it's going to radiate 1 rudi. Now, if you have an atmosphere, the atmosphere can pick out some fraction of that, the fraction that I just called A here for absorption. And it picks up that absorption. And so then what goes on through the atmosphere is 1 minus A. So if A is 0.2, we're going to absorb 20% of what comes up from the Earth. And we're going to radiate, and we're going to just send on through the atmosphere, unimpeded by the atmosphere, 80%. But this 20% heats the atmosphere. And any body that is heated becomes a radiator of electromagnetic radiation. And so you can imagine this just as a thick slab of atmosphere, and it's going to radiate away the A fraction, the 20% that came in. 10% will go out this way, and 10% will go down this way. And that's the crucial thing. That's your greenhouse effect. 10% is going back into the Earth. So, let's say in the next second, here comes another unit from the sun, but now it's got 10% more energy to get rid of the unit that's coming from the sun, plus it has to get rid of the 10% that has come in from the atmosphere. And here, I've done this in a little table. This is maybe more table than you like, but along here in the table, I'm talking about, so I changed the units. So now we're doing, we're doing 20,000 albans, all right? And they're coming in from the atmosphere. So what goes in this column is what comes in from the sun, that's the circle with a dot in it, to the Earth, plus what comes in from the atmosphere to the Earth. And so I'm going through a sequence of time intervals. And in the end of the first time interval, 80%, remember, just goes off to space. But 20% of 20,000 is 4,000. And that's absorbed. And then 2,000 of it escapes. So the total escape is 2,000 plus 16,000. That's the 18,000. And then 2,000 goes back to the Earth. So now for the next interval of time, what we have to get rid of is the next 20,000 that has come in from the sun, plus that 2,000 that's come down from the atmosphere. Now, you can go on doing this for a while, but what you need to notice is if you got 18,000 escaping and you got 20,000 coming in, you got global warming. Anyway, you got warming. And so, but what you can see is happening is the surface is getting warmer. So now it's going to send 80% of 22,000 away. It's going to send 20% of 22,000 into the atmosphere, which will send half of that away into space for 19,800 and 22,000 or 2,200 back to Earth. So the next time we got 2,000 plus 2,200. Well, I don't want to go on doing this too much longer. So the key thing is we had this 20,000 and the Earth has to get rid of it. And it couldn't get rid of it until it warmed up, because that's what's happening as you add energy back from the atmosphere and go through a few cycles. And you end up finally, after only 5 cycles, you see we've come almost to equilibrium. By warming up the surface of the Earth, we're able to push enough energy out through the atmosphere to equal what's coming in from the sun. And the price for doing that is warming. That's the greenhouse effect. It's called the greenhouse effect. It's misnomer. Greenhouses don't work this way. This is more, I think this is more like a blanket effect. It's like getting in bed and you put on a blanket and it, it keeps you warmer. Um, but uh, but the heat goes out the top of the blanket and goes away. And if you think about it, you can add another blanket and you'll be warmer. And so thereby sort of lies the next tale. This is clearly way too simple. But you see how it works? I hope. But, does it work on all the planets? Uh, let's look at the effects of the atmospheres. And you remember, uh, Venus and Earth, and I've added Mars, have very different atmospheres. Actually, the Mars atmosphere doesn't look so much different from the Venus atmosphere. The one that looks really different is the Earth. And we talked about that last time. I mean, that's a wonderful thing. That's because there is life on this planet. Otherwise, you would not have 20% oxygen. And I don't know if you would have sort of 95% CO2 that you have both in Mars and Venus. I mean, you can have a huge percentage of CO2, but on Mars, it's in a much thinner atmosphere. Still, here's something worth looking at. Let's look at the partial pressures of of carbon dioxide on the 3 planets. And so here's what it is on Earth. Earth has an atmospheric pressure measured in kilopascals. That's a bar. That's 1,000 pascals. You don't really need to know what a pascal is. It's a Newton per square meter and some stuff. But what you do need to appreciate is this 101,000 of whatever these are. That's Earth's atmosphere. And the part of the Earth's atmosphere that's carbon dioxide, that's only 40. Not 40,000, just 40. So you got a Earth with 101,000 pascals. Earth carbon dioxide in that atmosphere is 40 pascals. Well, Mars, which has an atmosphere of only 160th of an atmosphere, has an atmosphere of about, what is it? I guess it's about 600. Well, yeah, it's about 610 pascals. Again, Earth 101,000 and Mars 610. And of that 610, 580 is carbon dioxide. So if we will expect to see a greenhouse effect on Mars, and we see one on the Earth. Now, Venus, a little different. The partial pressure of CO2 on Venus is 8,800,000 pascals. We're in a very different world. And what I had hoped to do when I got involved in this, and I blame John Rudy for it because he was saying, people should talk about something they don't know anything about. And I thought, great, I can think of one of a number of places where I qualify. But this is the one that I chose. I thought I would like to understand the greenhouse effect on Venus. And in the end, I'm not particularly satisfied. But let me pass on to my dissatisfaction. Clearly different amounts of CO2 and clearly different temperatures. I mean, remember, this is 500 and some, 540, I forget the numbers, but I should have written them down on the table. They're nice. This is 288, and this is considerably cooler. Still, none of these does the simple black body temperature without an atmosphere. It's clear that in each case, the atmosphere is important. So I thought, here's what I could do. And this is not my idea. The idea is, let's replace the one-level atmosphere with multi-level atmosphere. And This is a picture I stole out of it, where I thought, when I saw it, I thought, yeah, I can do that. Because they've got these functions and they got things going on here. And the straight lines are stuff that's just going through the atmosphere and escaping, like we were seeing in my little one-level model. And the wiggly lines are absorptions at different levels. And one of the things that that I begin to realize, partly, or I should have known for years, is our atmosphere is actually quite complicated. And the complexity of the atmosphere has a lot to do with just how the so-called greenhouse effect is going to work, just how these blankets are going to keep us warmer. And it turns out to be, at least for my purposes, too complex for me to do with simple mathematics. And in fact, as near as I can tell, it's too complex for anybody to do with simple or even reasonably complicated mathematics. They end up having to build these large computer models, which maybe you will hear a little bit more about in what follows me. So we have, it's the complexity of what goes on in the atmosphere that beats me. And yet there are some insights, and one that I can show you, which I think is beautiful, comes from this picture. Now, I said the atmosphere is complicated. This is the Earth's atmosphere, and it's supposed to show you along this axis the temperature. I don't know if you can read these numbers, and the picture's kind of blurry on my screen. And here is the height in kilometers. And so the atmosphere, our atmosphere, divides up into something which is not shown here, which we call the boundary layer. It's not very thick. And then there's the troposphere. And the troposphere is the part of the atmosphere that's well mixed. It's where the weather is, it's where the clouds are. And it's up to about 10 kilometers. It actually varies with latitude. At the equator, it's higher than it is at the poles. But one of the characteristics of it is, and physics can explain this, as a packet of air of a certain temperature rises, well, if it's warmer than the surrounding air, a packet of air is like a balloon, and it will rise. And it will also expand, and then expanding, it'll be pushing against the air around it, and it'll be doing work, and it will be losing energy, and it will cool. And so the characteristic of the troposphere is that the gases of the troposphere, the atmosphere, cool as you go up. And they cool at about, I think it's about 10 degrees per kilometer. So that by the time you get up to 10 kilometers, you're going to be close to 100 degrees cooler than you were at the surface of the Earth. Well, maybe I've got that wrong, because that sounds too cold. But there's a lot of cooling going on. And we'll come back to that in a minute. And then it turns out that the atmosphere starts to warm again, mainly because of ozone, I think, and picking up temperature. And then you get into a place where the stuff just gets affected by solar UV that doesn't get through to the lower parts, and affected by cosmic rays and even X-rays and stuff. So the point I just want to leave you with is our atmosphere has a complicated structure, and that complicated structure has a strong influence on the warming of the surface of the Earth, on the greenhouse effect. Now, let me show you one of the effects. So we know there are so-called greenhouse gases. There are gases that do the absorption, take the energy out of what's coming up from the surface of the Earth. And if you go to the top of the atmosphere, and this is actually observational data, I showed you this last time. If you go to the top of the atmosphere, what you see is, again, here's the radiance in watts per square meter per, well, you don't have to worry about this, the radians, but watts per square meter per wave number. So a little stripe of this stuff on here, the area under a little stripe of this is going to be an energy being brought to this site by radiation of the wave number down below. And you notice here we are at 667, or right around 700. This is the wave number at which, one of the wave numbers at which carbon dioxide absorbs. And you can see if we're standing out of the upper atmosphere, we're seeing radiation come out, but we're not seeing nearly as much radiation come out at 667 wave numbers as we are over here. This is wave numbers, so-called atmospheric window for the infrared. It can come out. And remember, I told you this is actually satellite data taken over the Sahara Desert at near noon. So it's bloody hot. You know, that you take 273 and subtract it from that, and you're going to get something in about 40 Celsius. And that's that part, we would say, oh, that's coming from black body radiation of 320 Kelvin. And it is. It's coming from radiation from probably barely a few centimeters, a few inches, if you like, above the surface of the Earth, where under a noonday sun in the Sahara, this is the real temperature. And you see there's absorption going on in other places because there are plenty of other greenhouse gases. And I haven't talked about water vapor. Water vapor is extremely important. And the fact that there's nothing getting up from 320 Kelvin is because the water vapor is absorbing it. Now, and here's ozone doing the same thing. And here's methane doing the same thing. These are the greenhouse gases, and they are affecting the distribution of radiation that you see at the top of the atmosphere. But I like to just point out one kind of, I think it's rather pretty feature of it. You'll notice that the carbon dioxide is still coming out, but it's coming out as though it were coming from like about 240, 260, so about 220 Kelvin. See this dashed line here. All these lines are the black body radiation curves of a succession of temperatures, and they go up in 20 degree steps, 20 Kelvin steps. And this one is coming from something rather cold. So what you can see is happening in this mechanism of greenhouse effect is that the first level of the atmosphere absorbs it, re-emits it to the second level, re-emits it to the third level. But as you're going up in the atmosphere, the pressure is dropping and the amount of CO2 is decreasing. So as you go from level to level, your absorptivity is going to change. Also, it's getting colder as you go up until finally you're going to get to the top of a column where there's enough CO2 above you to continue to absorb this absorbed and re-emitted radiation. And so finally, this top level will say, okay, here I'm radiating and nothing stops me, and away I go into space. But I go into space as though I'm radiated from whatever the temperature at the top of that column was. So that takes you back to what we were seeing in the previous curve. We're sort of going up here, and by the time we get up here, there is no longer enough carbon dioxide above us to do the absorption, and so we start getting radiation from that point. Very pretty, I think. And finally, or you see that it has this spike in the middle. This is also kind of nice. The spike is actually a more where the CO2 most strongly absorbs. I mean, it is right at the middle of a range of wave numbers at 667. CO2 has a very high probability of absorbing radiation of that. And so even though you've got to a point where there isn't enough CO2 above you to absorb anything that's radiated from the wings of this, in the center, the amount of CO2 that is above you is still enough to absorb that spike. But look what happens if you go back here. You see, once we get through the tropopause, we start to rise in temperature again. And so now the spike is being radiated from some point up in the stratosphere where the temperature has risen some. And so you're seeing the spike come from somewhere between 220 and 240. You know, it's like 235 or something like that. Anyway, I thought that's very pretty. Something similar like that is going on with the ozone, except again, in prettiness, this spike actually represents a place where the ozone is ineffective as an absorber. And so this spike comes from something that down near the surface, which has a temperature of around 300 Kelvin. So this is really coming from the lower atmosphere. But you can go through and make all these arguments about what's happening and who's absorbing what. The point I want to leave you with, though, is that those were observational data. These are calculated data. And I'm showing you the same thing again. I'm showing you here at 230 Kelvin, and here's our carbon dioxide dip. Here's our carbon dioxide peak, which is coming from 255. Here we are at the top of the atmosphere. Here's our 294 sort of surface temperature. All of these jiggle-jaggle things here are water vapor and the other gases. So we can calculate a lot of stuff. And that, in a way, brings me to the my conclusion, which is, yeah, we can calculate a lot of this stuff. And in the end, it turns out that the complexity is so great that that's the only way we can figure out what's going on, because we have to calculate the energy flows into the different strata. We have to understand what the absorptions are in great detail of the different greenhouse gases. There are other mechanisms that are adding energy to the troposphere. The Earth has convective clouds. I mean, warm air rises and heats the atmosphere. Water vapor goes up and condenses and releases a lot of energy. All of these things heat the atmosphere. And in order to really end up understanding how important the different greenhouse gases are, you have to do these calculations. And the only way we know to do these calculations is by computer simulation. And so computer simulation becomes the central issue of everything we're doing here. I just point out that Venus also has a temperature curve, very much like the Earth's. I mean, it has some kind of a troposphere here, and has some kind of a stratosphere here, and then something cools, and then Venus does some stuff like we never saw anywhere else, and we don't really understand it. But the point I just want to assert is complexity of the atmosphere makes us totally dependent on computer models for understanding what's going on. And here is a slide which I think is quite nice, just to remind you that this is true no matter what planet we are of the three we've been talking about. We talk about here are measurements of radiation at the top of Mars atmosphere. Huh, does that look familiar? You know, here's another version of what I showed you before for Earth with its carbon dioxide dip and its ozone dip. And here is what it looks like for Venus with a lot of absorption going on, a lot more CO2 absorption going on. That makes sense. But as I said, what I like as a physicist is I want to be able to calculate something. I mean, I love that single level model because I get to put some numbers in and see the numbers go through and change in the way that they ought to change. And I like that. That's fine. And I can't do that here. And that's very disappointing. But I think no matter, I have to go along with what I think is the consensus view that for whatever reasons in detail, CO2 is really important. And I think with that, I just conclude and then turn this over to my my collaborators in the study group. We studied earth science, climate science course from Penn State for 12, 13 weeks, and it's a lot of fun. But I can answer some questions, and let's see, let's chat. Yeah.
Charlie,
Yeah.
can you go back to that the color slide that showed the temperature change through the atmosphere going up, the zigzag one?
This one?
No, back about
Oh,
3 slides.
incidentally, that's what these little things at the side are. They're showing you how the atmosphere changes in temperature in all those 3 places. Yeah, this one?
Keep going. Keep going back. Keep going.
This one.
There we go. Yes. All right. So I'm looking at this, and silly person that I am, I believe that as we go into space, it gets colder.
Well, you see
what
happens.
What you're showing here gets warmer. So there's something that's not computing in my head.
Okay. So you have to understand the definition of temperature is the kinetic energy of the particles. So if if you have one particle and he's moving very fast, he's hot. If you have and what's happening as you go up here is your density is drops off roughly exponentially. So that by the time you get up into the ionosphere, which I guess they no longer use that term. Anyway, you get up in the ionosphere, the particles are getting so far apart from each other that there's, if you step outside, they're not going to keep you warm. First of all, you'll die because there's nothing to breathe. And secondly, you'll die because it is cold. You will be radiating tremendously. But if those particles bump into you, they're moving quite fast. And so they have a high temperature, we would say, even though it won't, the amount of heat that's there in a volume of space is so low.
So Charlie, could you say the specific heat is low?
Well, I guess so. I guess that's in effect what I'm saying.
Yeah.
All of these concepts that we're used to dealing with when we have mass in familiar densities become very almost useless as we get to talking about very tenuous atmospheres in which particles have long mean free paths. They go long distances before they run into each other. So I guess that's what I would claim.
Okay, fair enough.
Charlie, I have lots of questions, but I'm only ask one here.
All right, Dick.
Do you have any curves that show nitrogen, the effects of nitrogen on, because Earth has a lot of nitrogen?
Earth has a lot of nitrogen. And at the temperatures and pressures of Earth, nitrogen has not got much interaction with the radiation, with infrared radiation. Nitrogen is a diatomic molecule, so it's 2 atoms in a straight line. And such atoms typically do not absorb much infrared radiation. So oxygen doesn't, nitrogen doesn't, O2, N2, H2 won't, but CO2 is a 3-atom molecule. H2O is a 3-atom molecule with a strong electric dipole moment and is gung-ho to absorb infrared radiation. CH4, complicated also. N2O, which is a pollutant, will absorb infrared. And I have read, and interesting, and I would like to know more about it, but I've read that on some of the, I'm not sure whether it's some of the exoplanets or whether it's actually on some of the moons of Jupiter or Saturn, N2 is present in an atmosphere at such a pressure that it begins to be a greenhouse gas there, and may be why there could be surface water on some of the moons near the outer planets. Kind of speculation I like, but I like to check it.
Charlie, Larry speaking.
Yeah,
The slide that we're looking at, does that explain in part why it's so hard to deduce the temperature on Earth from satellites? Because those folks were doing it wrong for a long time before, especially the people, where is that, Tennessee, that were way off for a long time.
I don't know about that, Larry. Tell me more. Do you know? I mean,
Well,
I think that,
the people that were deducing temperature on Earth from satellites, but I think it's at Tennessee where one group is that monitors one satellite, were saying that global warming is not nearly as rapid as other people were saying, and they were trying to deduce the Earth's temperature from satellites.
oh, I see.
And from what little I've read about it, there are so many corrections that have to be made. And maybe it's because they have to go through all these different gyrations that you just explained, that they had trouble getting the right temperature on Earth.
Well, I mean, I have read some of the.
Finally, after about 20 years, they got it close to right.
Yeah. Well, I have read some of the papers, and the kind of corrections that I found astonishing. I mean, the kind of minutiae you have to worry about have more to do with the environment of the satellite as it's receiving its data from Earth. The angles are crucial. The presence of nearby warm parts of the satellite is going to affect it. I mean, they're emitting infrared radiation and so on. And you go through, as you say, a lot of corrections. And I don't think those are corrections for what's coming. I mean, I think those are corrections to your instrument. But
I was told by someone in the business that they profile the temperature down to the Earth from the satellites by communicating through the satellite from one satellite to another, so that they're going through various altitudes and distances through the atmosphere. And it's so accurate that from this information, they can deduce the temperature everywhere between the satellite and the Earth.
well, I think that's consistent with Larry's statement that it's taken them 20 years to learn to do that. Yeah.
I think another thing they were running into trouble with was the distribution of water vapor, and they weren't taking that into account properly early on.
Well, again, because water vapor is an enormous, the condensation of water vapor releases a very large portion of energy that warms the different strata. Yeah, but that would only be true up to not even probably all the way to the top of the troposphere. Still important. I mean,
But it's enough to affect how you predict global warming.
you bet, you bet.
However, you can measure the ocean temperature from the satellites. And
Again, that's tricky.
yes, it is tricky, but what they're looking at is the reflectance from the waves on the surface. By interpreting them, you can tell what the wind is, what the wind speed is. And let's see, well, that gives you the wind speed, but they also have a good way to measure the ocean temperature, which is of course crucial.
Yeah. So that's all of the remote sensing is a wonderfully arcane business. I remember reading one of the early Landsats. Well, I think they wanted to classify the data coming in from the Landsats because they could detect a change in water level on the surface of the ocean with such precision that you could tell if there was a submarine below the surface. You could actually track American nuclear subs from their perturbation of the water surface, even when they were deeply submerged. I'm easily impressed, but I'm impressed by that.
That might have been an interesting question for Mike Perlman when he was here, when he talked about geodesy and how they do measurements from space and stuff like that.
That's right. Oh, well, yeah, there's a lot of neat stuff like that. Okay.
Interesting trivia question from me. We talked about ocean temperature.
Mm-hmm.
What is ocean temperature? Is it the temperature of the ocean at a certain depth, the surface temperature? You know, what does all that mean? I hear it and I understand it, but physically, what is it?
Well, I think It's an excellent question, Peter, but I think we would like it to be all of those things, you know. So I have to, whoever's telling me the ocean temperature has to tell me, is he telling me the surface temperature? Has he penetrated to find something going on deeper down? I think that's very hard.
Well,
Yes,
there's also the so-called ocean temperature or the temperature on the Earth are constructed averages. I mean, the ocean temperature is obviously going to be different in shallow water than it's going to be in deep water, and it depends upon it depends upon where it is and what currents there are. And so these are all global averages of one sort or another. And it depends whether you want to believe it or not, depends to a large extent about how consistent things are. And the changes are probably more valuable than the numbers themselves. Because at least if you agree on how they're going to be measured, the changes will vary less than the absolute numbers themselves.
Yes, I believe most of the observed ocean warming is really relatively near the surface, and not much when you get deep down.
That's my understanding as well, Carl.
More recently, they have studied in the North Atlantic temperatures at various depths, and they've determined that the North Atlantic drift is weakening by measuring temperatures farther down. And that has a serious impact on their predictions.
Okay,
Well,
I'm going to stop sharing unless anybody wants to see any more of my slides. And, we turn this over to, I guess we didn't ever talk about any order, but it was the three next speakers ought to be Mike, Jerry, and Carl. Jerry always likes to go first, so we'll let Jerry go first.
Okay. So what I wanted to discuss was the movement, the movement of heat. I got all this share thing. Let's get this out of there. The movement of heat through in the climate. I didn't understand how the climate worked, which before you start saying this climate change, it's probably appropriate to know how in the world it works. And you can see that it's not a simple thermocline where you have, can you see my cursor?
Yep.
Where you have a band of heat at the equator and then it gradually just goes smoothly to the North Pole. It is not a black body. And you have like here along the coast of Argentina, I guess it's cool up to here. You have flares of heat going up. You have flares of cold coming down. And then you have the seasons of the year. So it's a very complicated system of movement of heat. And
that's why they call it chilly, Jerry.
There you go. Heat. How do I change this slide to the next? Go to the next slide.
Top over there. You had it open. You had the flipped open. There we go.
Just hit your left or your right arrow.
Oh, maybe I'll try that. But here, I just want to give a few terms which Charlie alluded to. Heat being the thermal energy of a body measured in joules. For each atom or molecule, it is important. The kinetic energy is 1/2 times the mass times the velocity square. And then the average kinetic energy, the vibration, is what determines the temperature. And the energy is just quantity. There's the ability to produce change in physical system, heat energy, and is measured in joules, which we all know. Let me see if I can, okay, now, power is the energy expended over a period of time. So when Mike Tyson hits you, he puts a lot of energy over a short period of time. And it's measured in watts per second. And that's basically what the heat flux is, the energy flow. And I put the temperature sort of redundant. I said that. And heat goes all which ways, which Charlie has alluded to, is going up, it's going down, it's going sideways, it's going everywhere. And the models are very complicated with a lot of assumptions. But what I thought I'd do, take you back a little bit to try to get it a little bit organized. You may remember from chemistry, the gas laws is pulmonologists do all this stuff. Gay-Lussac's law. Gay-Lussac, his family's name he was French. His was the Gay family, and they lived in the village of Lussac. So they put the name Gay-Lussac. Actually, they weren't simple villagers. They owned most of the village. They were the aristocracy, which certainly served them well until the French Revolution, then not so well. And you have Avogadros Law, which is, so the pressure is proportional to the temperature at a constant volume. So pressure equals some constant times the temperature. We have Avogadros Law, which the volume is proportional to this is nu, the mass. So the volume times a constant equals, volume equals a constant times the mass. And you mix them, put them all together, you get a pressure times the volume, this times this, equals another constant times the mass times the temperature, which is, you remember that, which is, if you call R, K is the ideal gas constant, then you get good old first year chemistry, PV equals nRT. And this is what drives the whole system. So the movement of air goes from higher pressure to lower pressure, higher to lower density. Volume and pressure being constant, cold air has greater density, more molecules than a warm gas. So the higher density is going to fall and the warmer is going to rise. And water vapor, this is really important. Water vapor reduces the air density, so it rises. And the way it does that, if you go back to the molecular weight, nitrogen, you recall, has 7 protons, 7 neutrons, so it's 14 molecular weight. And as Charlie said, it's N2, so it's 28, the molecular weight. Water has an oxygen, which is 16, and a hydrogen, which is 1, so it's got 8. So now if they're in a temperature system of equilibrium, then they will all have the same kinetic energy, but the nitrogen will have a lot of mass, so it makes it more dense, and the water will have a lot of velocity, so it contributes less to the mass in any given volume. So again, heat, volume rises, density falls, and the air rises. And this is a simple graphic of the same thing. Here as the density falls, the gas rises to a greater height. If it cools, it's going to come down. So now we get to the interesting part of how the atmosphere, I'm just talking about gas now, how it works. And what we have is these cells. This is the basic mechanism. Here is the equator here, and the gas gets very warm. It gets a lot of water from the ocean because it's evaporating, because it's hot. What does it do? It rises up to the tropopause, which, as Charlie said, it's the interface between the stratosphere and the troposphere. It's about 8 miles or so. It starts to get cold. So now it's got to go somewhere because it's rising. So it's going to go either north or it's going to go south. But it's getting colder. You're going to start to have some rain over here. You're going to have some rain over there, and it's going to get heavy, and it's going to come down at about latitude of around 30 degrees or so north, and latitude about 30 degrees south. And just keep going around and around, or it's going to go north along this route. So then we get another cell. They call it a feral cell. So the Hadley cell goes up here, gets cold, rain, more dense, comes down. Now it's denser, it travels pushed along the surface. Then it starts to warm up and get moisture again, not quite as much, and it rises not quite as high, goes this way, you get rain here, comes back down. It's either going to go this way or it's going to go north to an additional cell, which is called the polar Hadley cell. And if we look at, so now when you see these crazy diagrams, you look at this, what in the world is this telling me? That was my first reaction. Here is our Hadley cell. Forget all this part. This is where he shows it. Air comes up because it's hot and wet. It gets cold. It rains here. It's mostly nitrogen. Heavy, comes back down. Gets a little warmer, and picks up moisture. Goes back up, comes back down, and keeps doing that till it gets to the North Pole. And that's how the heat, the heat in the atmosphere, the warmer air, eventually finds its way north in a somewhat static system. But then we have the Coriolis effect. So we have cold air coming down from the poles, has no angular momentum, so the Earth is turning, so it's going to drift to the west. The warm air from the equator has a lot of angular momentum. You can see this is traveling at 1,600 kilometers per hour. This is traveling at 0. So it's going to drift to the east. So you have that as a mixing effect in addition to the Hadley cells going. So it's going up and down, it's going sideways. And then we'll get to the water. And this looks like a complicated diagram, and it is. And it's hard to understand, but here we have all these gyres. And this is the one that I looked at the most because it's something I understand because here's where we live. Here's the Gulf Stream here. And here is shown the warm water coming up and the cold water coming down. Now to look at, we're talking about the specific heat in the atmosphere. This is the specific heat. It's joules per kilogram per degree Kelvin. Air, its specific heat is 700. That's at 0 degrees centigrade is at sea level. It's a lot less, Peter, when it gets higher up because it has less density. So its specific heat goes way down. Now, if you look at that, look at water. It's 6 times greater per liter. But a liter of air at the at 0 degrees centigrade at sea level is 22 liters versus 1 liter. So it's 6 times more here, but it's also 22 times the volume. So it's about 120 times or so, maybe a little more, times more heat is contained in a liter of water than in a liter of air at the surface. So the water carries a lot of heat up north. So now, just like air, density drives water flow. And the things that I learned that increase the density of water is cold, of course. That has a major effect. And water gets very dense until it freezes, and then it gets lighter because you have what's called brine exclusion. So when the icebergs form, they're mostly fresh water with very little salt. So the icebergs float. But just getting water, liquid water, cold has a major effect, and salt has a minor effect. And so what they call this is the thermohaline circulation, because it's temperature plus a halide. I don't know how they figured this out, because it's the chlorine salt, sodium chloride. Why they didn't use sodium, I have no idea. But it's a thermohaline circulation. And if we just look at this, I thought I would start up here. Here, the water up here gets really cold. This is what Steve was talking about. It gets really cold and comes down because it sinks to the upper surface, which is down to about 400 meters. It sinks lower and gets heavier and starts to push down this way. It keeps pushing down and pushing down and pushing down. And something now, since this is pushing down, you create a pressure gradient. And so warm water is going to have its pressure gradient to go back up. And it just goes up and cools off and goes back down. And that's great if you're in a steady state. It will have its problems when you start changing that steady state. The other parts are explainable, but they're not as simple as this. This was the easiest one for me to understand. So the very warm water surface flows about the top 100 meters, and the deeper, cooler waters go more slowly. It takes about 1,000 years to make this crazy full circuit. And what we have in the North Atlantic is called the North Atlantic deep water, which I'll show you in a second. And heat is transferred from the water to the air. Now, here's an interesting factoid. 30% of the thermal energy received by the polar region is from the water going north. Now, to make it more complicated, oceans have updwelling and downdwelling similar to the atmosphere. And the downdwelling occurs where areas are cool or have increased salinity. So you get a downdwelling, and that pushes this water up here. So when you ask what the average temperature is, I don't think there's a question that makes any sense, because there's so many different temperatures. It's just too much. It doesn't tell you what's going on. The average temperature doesn't really tell you anything. But downdwelling, when the surface areas are cool or have increased salinity, and I just wrote, remember the Dead Sea is has high salinity, so you can practically walk on it. Now here is our Gulf Stream. Here's where the trouble begins. Here you have the water being cooled, and here's the North Atlantic deep water Steve was talking about, going down this way. It's being cooled and it's pushing this way. That is dependent upon this being very cold. And then this warm water comes back up here, loops around here. That's what the basic flow is. And that, again, up here, the warm water up here and the cold water go down here. Now, here's the problem. When you start to warm this area up, Steve alluded to, if you warm this area up, this is not going to be so cold. It's not going to push down so far, and this is not going to therefore have a pressure gradient to go up so far. Right now, as you know, Boston is about here, and London is substantially farther north than Boston, but much more temperate because this warm water is warming this up. If this doesn't flow in the same pressure gradients, it's likely it's going to start to meander. And you have all these ecosystems that are very much dependent upon these channels of flow for where they've grown, and it's almost inconceivable that all the elements of an ecosystem, if this starts to meander, that all the elements of an ecosystem can meander with it and be successful. It's just too much for them to evolve to the different changes. So if and when this occurs, they will have major effects on the sea stock here, and I can't imagine that they'll be good. But it's hard to know where this is going to meander to, and only time will tell. And that's what I learned on my vacation.
So I have some notes that I had made from the course on water, issues of water. And first, I want to point out that the IPCC, which is the International Panel on Climate Change, which is basically a collection of scientists from countries, or from many different countries, and who issue statements based on sort of scientific consensus. And they try to avoid really radical things because those probably aren't the consensus. But anyway, they said that water and its availability and quality will be the main pressures on and issues for societies and the environment under climate change. So in other words, not as much obviously temperature rising could rise enough to make things really, really uncomfortable. But I think they really think that this is going to be the big issue. And so the climate models, and again, I won't get into, I don't understand enough about how they work. I don't know whether or not anyone does, but seem to show that some areas that are already dry are going to get drier. Some areas that are already wet are going to get wetter. And both of those can be very, very problematic. And the US Southwest, uses a lot of water, and it is an area that seems to be drying. So the distribution of water on Earth is interesting. It's amazing how little usable fresh water there is. So of all the water on Earth, 97% is in the oceans, and that's saline. Obviously, we can use it if we desalinate it, but that takes a lot of energy, and that feeds back to the climate problem. Fresh water is 3%. And of this 3% of fresh water, almost 69% is in ice caps and glaciers. 30% is not. And then of the surface water, most is in lakes. There's some in swamps. I was very surprised as little as 2% is in rivers. Okay. In terms of where we in the US utilize water, which is not necessarily true about the whole world, but probably not completely different. It was surprising. 42% of our so-called freshwater withdrawals are for cooling power plants, of all kinds, coal, fossil fuel plants, nuclear plants. 32% is for irrigation.
Excuse me, Carl, but
Yes.
the water that cools a plant does not get dirty or contaminated from that cooling process, right? It merely gets warmer.
Yes, it gets warmer, and then it may go out into the into the oceans. Depends on where it goes to.
But
Some of it will go
theory,
into the air as it warms up.
In theory, I would assume, and I don't know volumes, I don't really understand the volumes, but it could go into cooling ponds or something. I guess my only point is that there's a big difference between water that is used in mining and gets contaminated, I would think, versus water to cool a plant.
Yes, but I think, well, that's true, but the water to cool plants, I don't think in any case is a closed loop system. It's taken from somewhere, and then it goes out to various places. It's dissipated in different ways. So if it's being taken from a river, you're well, if it goes back into the river, you're warming the river. There's issues there. So I'm not saying that all this water is lost, but this is where it's sort of being, what it's being used for. 32% is agriculture. So that's irrigation. 12% is what's called public supply. And that's basically all the water that you and I use for drinking, bathing, washing things, as well as all sorts of company usage. And then finally, there's this sort of self-supplied industrial, I think means that it's coming out of, it means industry other industry that's taking water, but it's not getting it through a public supply. So it's maybe getting it directly from a river or a lake. I have something here about the water cycle, again, which is very complicated. I'm sorry, this may be a little bit of an eye chart again, but water is evaporated out of the oceans. Some of it stays in the atmosphere. It comes down as precipitation of various sorts. A lot of it goes through the ground, and from the ground, some of it comes out back into the ocean. Some of it goes into rivers, which flow into the oceans. There's a question of a water table, which is the depth below which any space tends to be filled with water. And we have aquifers that are, water that are capped with impermeable rock, and that can be, if they may be confined that way or so-called unconfined. And essentially a lot of the world's water is coming from aquifers. And as it's being pumped out, the aquifer, in most cases, it's being pumped out much faster than new water can seep into the aquifer. And so aquifers generally are dropping. There's this idea of residence time, which can vary from a few days to 10,000 years or more. And that's the time that the water spends underground. But anyway, there are places where land is subsiding because aquifers are being depleted. I was amazed at this. There are areas of Central California that have subsided 10 meters in the last 90 years because of pumping out of the groundwater. There's also often problems with groundwater contamination. And China is one of the places that has apparently a very big problem, because China is relatively poorly watered for its size and population. There's water in the south. There's not much water in the north. They're working, they've been building giant canals to move water from the south to the north, including they have to cross rivers to do that. But they have a big problem of pollution of their groundwater. So I did want to mention something about places that are drying out. In Australia, the Murray-Darling Basin produces a third of Australia's food. It's always been generally dry, but it's been getting drier in recent years. And in many years, the Murray River no longer reaches the ocean. And a lot of this has been over-extraction, which is also a problem in the US, the Colorado River, et cetera. I brought in a little historical thing that wasn't in the course, but I happen to know about ancient Assyria was, conquered Israel in 722 BC. But from a period of 912, roughly 912 BC, up to about 605 BC, Assyria was the big kahuna power in the Middle East. It had a very spectacular rise and then a spectacular fall. And some studies from caves in the area show that the period when it was a great power corresponded to a very wet period. It was dry before and it was dry after. So this is about the effect of water on civilization. And I think that's probably enough. I'll just mention one other thing about, there's a concept of virtual water, which is water that is consumed to produce something. So, we consume virtual water all the time. It takes a tremendous amount of water to make one almond, for example. Cotton is a huge user of it. And there are many arid areas on the earth where they're producing these things and consuming large amounts of water. So I think I'll stop it there. So this isn't all about climate change. Much of this has been going on for a very long time. A lot of it is an issue of human overuse, but climate change appears to be aggravating it in some areas.
All right. Go ahead.
Two closing comments, because I didn't really talk about what I learned from taking the course.
Please do. You're up next.
All right, so two things that I learned from the course. One is that a lot of the issue, a lot of the consequences of climate change that people are worried about are almost indistinguishable from the consequences of overpopulation. We have an awful lot of people on this planet using an awful lot of its resources, and we're seeing the impact. That's probably the big lesson of all this, is that, this is the Anthropocene era, as someone has coined the term to mean we are now a major influence on the planet. And that I thought interesting. The other thing which I learned is the planet is just beautiful. I mean, my God, the intricacy with which the things work. We've been, as a species, rather slow to discover that. But the guys who are doing climate science now have been kind of slowly pulling it out of the depths of our ignorance. That the deep sea ocean currents, nobody even knew about those 50 years ago, and yet it turns out they're crucial. They move the heat around, they change the climate, and the balance and the intricacy of it all, it's just a marvel. I mean, it's just wonderful and worth, it's an emotional experience to see all that. At least it was for me, and I really like that. That's enough.
Well, it proves the concept. The more you know, the more you don't know.
Can I ask a couple of questions? I said I had a lot of questions, and can I ask two? Probably Charlie's the main one I asked this of. First of all, where does all the CO2 come from originally? In other words, we're concerned here in climate change, and our big culprit is CO2. So my first question is, where did the CO2 that is on Earth, Venus, Mars, and so forth, where did that come from originally? And then my second question is, why is it that the planets that are closer to the sun seem to have CO2 atmospheres, whereas those farther from the sun, from what I understand or remember, don't have CO2? They have methane and things like that.
So, I mean, I can give you kind of rough answers to both the kinds of questions, Dick, but maybe they won't be that satisfactory. I mean, the carbon and the oxygen, I'm a nuclear physicist by background. That was my field of specialization for years. And one of the things you learn in nuclear physics is a plausible explanation of where all the chemical elements come from. They come from nuclear reactions in stars. They're produced by a first generation of stars. We used to treasure the aphorism that we are all made of stardust, because the planets are formed from stuff that comes from second generation. That is, we had to have stars that blew up in nova and supernovae and created the elements. Now, when you know some nuclear physics, you go in and you look and you can predict what the amounts of the different chemical elements will be. And there'll be hydrogen, helium, and lithium, and beryllium, and boron. Sound like Tom Lehrer singing, but it's carbon and nitrogen and oxygen. Everything up through neon gets produced very kind of directly and simply and in relative abundances like we see in the universe. And so when you get your primordial planet formed, there's going to be plenty of carbon there, and there's going to be plenty of oxygen there. And now what happens to those in the chemical evolution of the planet, that depends. There's also going to be a lot of hydrogen, and therefore at some point there could be a lot of dihydrogen oxide or water, as you might think of calling it. But then you're into the geology of your planets and the size and what they can retain and how close they are to the sun. If you're close to the sun, your chances of losing your water are very high, especially if you don't have an atmosphere, because then solar ultraviolet breaks up the hydrogen, the water molecules, and then you end up with hydrogen in the upper atmosphere going away, and so your water goes away. So the role of the atmosphere again appears. I mean, you say, oh, maybe we have our water because our atmosphere was just right at the right time. Mars, we're not sure. They're now talking about, well, maybe the water is still there, but trapped somewhere else. Venus is probably just too close to the sun, and it probably over its evolution burned away, evaporated away its water. So
yeah, if you look at the temperature, if you look at the surface temperature of Venus, for example, it's way over the boiling point of water.
Well, it is now, yeah.
Yeah.
Yeah, that's right. Which a little bit begs the question, how did that happen?
Yeah.
But I would also add that after the nuclear physics explanation of the elements, or carbon, hydrogen, and oxygen are all very, very common. They're chemically reactive, and so the oxygen has tended to combine with the hydrogen and carbon whenever available to produce carbon dioxide or water. And again, as Charlie explained earlier, it's because of life that we see any free oxygen. Free hydrogen has a tendency to be lost because it's so light.